Hey guys, what's up? Today it's the first day of Eid and I've decided to work for you guys. Just wanted to show you that if you are aspiring to get something big, then obviously you need to work very hard. And this should inspire you to study as well. Yes, it is important that we celebrate Eid and you should, but also, take some time and do some studies as well. Anyways, guys, I'm going to be solving certain questions for you. These are all based on gravitational field. And the thing is that I'm going to be solving these questions because I feel personally, this is my gut feeling, that you are going to come across questions like these in the examination. So let's just begin without further waiting. I'm going to be turning off this camera because this will only be distracting you guys. Anyways, listen guys. So the first question is, state what is meant by the centripetal acceleration. Centripetal acceleration is the acceleration that is directed towards the center of a circle when something is moving in an orbit. The idea is that this acceleration should always be at 90 degrees to the tangential velocity of that object. So I'm just going to write this down. An acceleration which is always perpendicular to the velocity of an object, always directed towards the center of a circle, always directed, this is the second point, always directed towards the center of a circular orbit. Anyways, this is done. An unpowered toy car moves freely along a smooth track that is initially horizontal. The track contains a vertical circular loop around which the car travels as shown in figure 1.1. The mass of the car is 230 grams and the diameter of the loop is 62 centimeter. Be careful, look at the units. Units don't make sense. Apparently they do, but the problem is that we are going to be converting these units if we have to work something out. Assume that the resistive forces acting on the car are negligible. State what happens to the magnitude of the centripetal acceleration of the car as it moves around the loop from x to y. Oh my god. The idea is that what is going to happen is that this toy car is going to be moving towards the right. ये यहाँ पर पहुँचेगी. Oh my god. It's going to reach this position. उसके बाद this will tend to just go up. The thing is, initially it must have some kinetic energy. This kinetic energy is going to convert into something else because obviously there is going to be conversion into gravitational potential energy, but just be careful, this will still be moving over here. So some of the kinetic energy is going to convert to, some of it is only going to convert to the GPE, and this is how it's going to be moving, right? The main idea. So the thing is, it already has kinetic energy and this is going to be converting into gravitational potential energy. So that means the kinetic energy is going to be converted to something else. So kinetic energy technically decreases at this point. If this decreases at this point, that means the velocity tends to go down. The speed tends to decrease. So I'm just going to be working this out over here. The centripetal force. The question asks what happens to the magnitude of the centripetal acceleration of the car as it is. So centripetal acceleration is actually v square over r. Okay, r is the radius. So what we can do is that we can see that the relationship is very simple. This is actually the acceleration is directly proportional to v square. So if v goes down, that means the acceleration also tends to decrease. The the question is simply asking us to state it. So that means the centripetal acceleration decreases. Okay. Explain if the car remains in contact with the track. If the car remains in contact with the track, why the centripetal acceleration of the car at point Y must be greater than 9.8 meter per second squared. Okay. Explain the car remains in contact with the track. Why the centripetal acceleration of the car at point Y must be greater than 9.8? Oh my god. If it ain't greater, that means it is going to fall down. So I'm just going to write this down. If okay, must be greater than 9.8. If it is not greater, what is going to happen is that it will lose contact somehow. Okay, at the top position, at the topmost position, we can see there is going to be a reaction force. There is also going to be the weight, and together they make up Fc. So Fc is equal to W plus R, weight plus the contact force, right? So Fc, the centripetal force, is actually equal to the weight plus contact force. So Fc should be larger than weight. So Fc should be larger than weight. This has to be larger than this value so as to provide the contact force. So as to provide contact force, right? So Fc should be larger than weight so as to provide contact force. Therefore Fc should be greater than 9.8 meter per second. Sorry, acceleration AC should be, because the question deals with acceleration, but then again it is actually dependent on Fc. So AC is directly proportional to Fc. So AC should be greater than 9.8 meter per second squared. This is how you do it. Okay, this is done. Let's just move on to the next part. The initial speed at which the car and B moves along the track is this. Determine whether the car is in contact with the track at point Y. So the thing is, what we are going to be doing is that we are going to be finding the acceleration at the extreme top. Okay guys, so I have updated the microphone to something better. Anyways, the initial speed at which the car and B moves along the track is this. Okay, this is the initial speed, 3.8 meter per second. Determine whether the car is in contact with the track at point Y. So, समझ में तो आ ही गया होगा. That is what we are going to be doing. What we are going to be doing is that we are just simply going to find the acceleration at the top. Fc, we are going to find the acceleration, centripetal acceleration at the top. If it exceeds 9.81, that means this would be in contact. If not, then obviously it's going to just simply going to fall down and crash. Anyways, let's work it out. The initial speed is actually 3.8 meter per second. So, first of all, we are going to focus on the energy conversion thing. And initial energy is going to be, I'm just going to write it down. Initially, Ke should be equal to half mv square, right? And at this position, at position Y, this kinetic energy is going to convert to a new smaller kinetic energy, so Vy square, and that plus the mgh as well. This equation is very important because you can clearly see that in this expression we had initial kinetic energy. This actually, some of it actually converted to this. So this is less than this value, right? तो अभी इसके अंदर सबसे बड़ी चीज़ ये भी एक नज़र आ रही है that we can see clearly is that the masses simply cancels out. So this is going to be 1 over 2 v square is equal to 1 over 2 vy square plus gh, right? यहाँ भी पहुँच के we just reach this position and then we are just simply going to input the values and work this out. So this is going to be 1 over 2 into the initial speed is actually 3.8. square, this should be equal to half times Vy is something that we need to find out, and plus 9.81 multiplied by the height gain should be 62 centimeters. So this is going to be 62 into 10 raised to power minus 2. Okay, so this is what we are going to be doing, and we can work this out. So let me just work this out. This is going to be 0.5 multiplied by 3.8 squared. Okay, then we are just going to subtract this by 9.81 multiplied by 62 into 10 raised to power minus 2. We subtracted this, we just multiplied by 2 again, and then we are just going to find the square root of this operation, and this gives me Vy of 1.51 meter per second. Okay, yaad to pahunch gaye. So I'm just going to copy paste this. Oh my god. So I'm just going to copy paste this, and I'm just going to paste it here, and this should become this. Yahan tak to pahunch gaye. And eventually I'm just going to get rid of this, and finally we'll work out the acceleration. So acceleration is actually v square over r, and centripetal acceleration AC should be equal to 1.51 whole square divided by the radius is going to be 62 divided by 2 multiplied by 10 raised to power minus 2, because we need to convert this into meters, right? So this should become, I'm just going to be calculating this, 62 into 31 into 10 raised to power minus 2, and 1.51 whole square divided by answer gives me a value of, so AC is actually equal to 7.4 meter per second squared, which is less than 9.81 meter per second squared. So contact is lost. So contact is lost, right? Contact lose bhi ho gaya. And I can explain this idea, that is Fc is equal to R plus W. So if this force goes down compared to this, there is no reaction force, so no R, so no contact force, okay. So this is done. Anyway, suggest with a reason but without calculation whether your conclusion in C would be different for a car of mass 460 gram moving with the same initial speed. Well, apparently there won't be any difference, because we have the equation with us, which is actually 1/2 v square. Oh my god, आधी से ज़्यादा तो चीज़ें कॉपी नहीं हुई थी इसमें. खैर, I'm just going to erase this. So I'm just going to write this equation down again. So this is going to be 1/2 v square actually is equal to 1/2 Vy square plus GH. This was the equation, right? No. Whether your conclusion in this, it won't change. No change would be seen. Mass has no effect. So would be different for a car of the conclusion. So conclusion independent of mass. I should have written this, independent of mass. This is done, right? Let's move on to the next question. Okay, this is another question that deals with the same thing, but with reference to velocity and acceleration, describe uniform circular motion. We can answer this question very easily. With reference to velocity and acceleration, describe uniform. This is the exact same answer that we just wrote earlier, so it just begins with this fact that acceleration, let's just reduce the thickness. Acceleration is always perpendicular to the velocity. Acceleration is always perpendicular to the velocity. Acceleration is always directed to the center of the circular orbit. Okay, so that does it. Two cars are moving around a horizontal circular track. One car follows path X and the other follows path Y. You can see, look at this diagram over here. So we have path X and path Y. Okay, and the distances are given to us on this diagram. We can clearly see that this distance is given to us, and this is additional 27 meters. Okay, so we have the start and the finish line is given. Okay, the radius of path X is 318. I'm just going to zoom out a little bit so that this is much more visible. Anyways, look at this thing. Listen, this is given to us as this, the radius of the path X. Okay, so path X, this is the one. Okay, I'm just going to color this line so that it becomes more clear. Path X, I'm just going to mark this as the blue line over here. So I'm just going to draw a circle over here. Okay, so that does it. And similarly, I'm just going to identify path Y by a red color. So there it goes. And that is pretty much it. Okay. Path Y is parallel to and 27 meters outside. We have already have this distance over here. Both cars have mass of 790 kg. The maximum lateral sideways friction force F that the cars can experience without sliding is the same for both cars. Okay, so that means the frictional force is the one that is going to keep them moving in a circular orbit or circular path. The maximum speed at which the car on path X can move around the track without sliding is obviously 94 meters per second, which is given to us. Anyways, calculate F. Our target is to calculate F. So we need to calculate F, and the maximum speed, we have the speed with us, we have the data with us, which is 94 meters per second, and this is for path X. So the radius is given to us as 318 meters, and we need to find F. So, and do we have the mass with us? Well, the maximum we can work with, we have to calculate the force. Yeah, we definitely have the mass with us. So therefore, F is equal to m v square over r is going to give us the answer. We can calculate F. So this would be, the mass is given to us as 790 multiplied by the speed, which is 94, square divided by the radius of the path, which is 318. So this is going to be 318, and we can pull this off easily. Let me just calculate this thing. Okay, so I'm getting a value of 21951 Newton. Well, since the remaining values are all the minimum number of significant figures used is actually 2, so I'm just going to round it off to 2 significant figure, which should look very nice. 2 and that is 3 zeros newtons. So that does it. Okay, so let's just move on to the next part. Okay, let's move on to the next part. Both cars move around the track. Each car has the maximum speed at which it can move without sliding. Okay. Complete table 1.1 by placing one tick in each row to indicate how the quantities indicated for the car on path Y compare with the car on path X. So first of all, we are going to be dealing with the centripetal accelerations. This is the first part. So as we studied from the previous question, both have the exact same frictional force. The maximum lateral frictional force that the cars experience is the same for both cars. And this is the force, this is the frictional force which is actually providing the centripetal force, right? So that means if the frictional force is the same for both the cars, therefore the centripetal forces are exactly the same. If the centripetal forces are exactly the same, that means the acceleration, the centripetal acceleration would be the same. So this is going to be y same as x. Yes, this is the fact then, right? Let's talk about the maximum speed. Let's talk about the maximum speed. So for maximum speed, what we can do is very simple. The idea is that we have this equation with us. We know that f is actually constant. This is actually constant. If this is constant, that means mass is also constant for both the cars. So this would mean v square is directly proportional to r. And for y, the path y, the red one over here, you can clearly see that the radius is larger. If the radius is going to be larger, that means the speed is going to be larger. So y should be greater than x. We are going to mark this as this. I hope this is clear, right? Next step, the time taken for one lap of the track. The time taken for one lap of the track. Once again, we can construct an equation. So let's see. We have f is equal to m r omega square. So f is equal to m r. This is going to be 4 pi square divided by t square. And we are just going to identify the constants over here. This is a constant, this is a constant, and this entire value is a constant. So we can see that r over t square is equal to constant. So that means r is equal to t square, or sorry, r is directly proportional to t square. That means if the radius increases, that means we know that for y the radius is greater. That means the time period should also increase, and therefore I'm just going to mark this as y greater than this. I hope this is clear. Okay, so let's move on to the next question. State Newton's law of gravitation. I'm just going to write this law down. Okay, so this is the one that I have written for you guys. I'll just read it. Gravitational force of attraction is directly proportional to the product of the two masses and inversely proportional to the square of the distance between the centers of the 2-point masses. Two masses or 2-point masses. If I'm using the word 2-point masses, then I don't need to mention the word centers over here. So the idea is that if we have mass m and we have another mass over here, so this is the distance between the centers of the two masses. Okay, so this would become f is directly proportional to m1. This is m1, this is m2, and let this be r. So m1 m2 over r squared. I hope this is clear. Next step, the next part reads, use gravitational Newton's law of gravitation to show that the gravitational field strength at a distance r from the center is given by this expression. So we know that G is actually equal to the force per unit mass. So I'm just going to write it down like this. Actually per unit mass. And we are just going to expand this. So F itself is actually equal to the gravitational force of attraction. That means G m over r square. And then this entire thing is divided by m. This is the expansion over here, right? So this part is this, and the m is over here. And if we simplify this, we get g is therefore equal to gm over r squared. So this does it. Okay. Now the question says the earth has a mass of this and a radius of this. Okay. The moon has a mass of this and a radius of this. The earth and the moon can both be considered as point masses at their centers. Okay. That means the distance is quite large. Their centers are a distance of this apart. Okay. Show that the gravitational field strength at the surface of the moon due to the mass of the moon is this. Gravitational field strength is required at the surface of the moon due to the mass of the moon is this. We need to prove this, right? So let's just pull it off. G is equal to gm over r square. And therefore, this is going to be 6.67 into 10 to the power minus 11 multiplied by the mass of the moon is given to us, which is 7.35 into 10 to the power 22. And then I'm going to divide the distance. Distance is going to be the surface of the moon, and that is going to be the radius of the moon itself. So this is going to be 1.74 into 10 to the power 6 whole square. I'm just going to solve it. So after inputting the values into the calculator, I'm getting 1.619, so 62 Newton per kg. So that is proved. Next step, explain why there is a point X on the line between the centers of the earth and the moon where the resultant gravitational field strength due to the earth and the moon is 0. Okay, so there we have it. We have a null point, right? So that means I'm just going to mention the first step is going to be the null point. Explain why there is a point X on the line between the centers of the earth and the moon where the resultant gravitational field strength due to the earth and the moon is 0. Okay. This is going to be the null point. This is the null point. At which gravitational field strength this is the null point at which gravitational field strengths from earth and moon are exactly equal in magnitude and opposite in direction. So yeah, this is something that you need to memorize, what happens at the null point. Memorize it right now. Okay, let's move on to the next point, next part. Calculate the distance x of point X from the center of the moon. Okay, so we need to pull this off. We need to find the null point. We need to identify the null point, and this is going to be measured from the moon. So yeah, let me first draw the diagram over here, and then I'm going to explain it. Okay, so let me explain this idea. The thing is, first of all, I want you to focus on this green line over here. This is the distance between the centers of the. This is the distance between the center of the Earth and the center of the moon. And this is the distance x that we need to find out. So that means from Earth up to this point x, the distance is going to be 3.84 into 10 raised to power 8 minus x. Okay. So what we are going to be doing is that at this position, from the previous discussion, the gravitational field strength of the Earth and the Moon are exactly going to be equal and opposite in direction. So we are just going to do that. So therefore, I'm just going to be writing this down. G due to the Earth should be equal to G due to the Moon. And we're going to pull it off. Let's see what happens. And I'm just going to solve this. So therefore, calculate the distance x from the center of the moon. Okay. Calculate the distance x. So let's just do this. So let's just solve this question. So this is going to be the gravitational field strength from the Earth itself is going to be, I'm just going to work this out. So this is going to be G ME divided by 3.84 into 10 raised to power 8 minus x, and this is going to be G multiplied by the mass of the moon and divided by x whole square. So we have squares on both sides, and we are just going to solve this. So give me a minute, I'm going to solve it and let's see what we are getting. Okay, so look at the calculation that I have done over here. These are the masses that I have input over here, and after that I just try to get rid of the square over here. For that I use the root operation, and once that is done, I eventually got to this part, and we just move this x to that side, and therefore there is going to be an addition over there. So after that we just divided it and we got the answer. So I'm sure this answer is going to be correct. Anyways, this is going to be 3.8 into 10 raised to power 7. Next step, let's just move on to the next question and let's see where we are. Okay, define gravitational potential at a point. Well, this is an easy one. Gravitational potential is the work done in moving unit mass from infinity to a point. Infinity is defined as having zero potential. Okay, memorize this. Okay, starting from the equation for the gravitational potential due to point masses, show that the gravitational potential energy EP of a point mass m at a distance r from another point mass m is given by this expression. So what we need to do is we need to find the gravitational potential energy of a point mass m at a distance r from another point mass m is given by this equation. So first of all, let's define this symbol as the gravitational potential, and this is equal to minus gm over r. So this is actually the gravitational potential. I need to write this down, this is important. Gravitational, okay, very carefully, gravitational potential. Okay, so this is it. फिर उसके बाद हमारे पास क्या है? At a distance r from another point mass m. Okay, so the distance itself is given as r. So gravitational potential energy is equal to phi multiplied by m. So therefore phi m is equal to minus gm over r and multiplied by m on both sides. So we have it. EP is finally equal to minus gmm over r. That does it. Okay. Next step. Oh my god. Figure 1.1 shows the path of a comet of mass 2.2 into 10 raised to power 14 kg as it passes around a star of mass whatever that we have. Okay, so we have a star of mass. At point X, the comet is 8.44 meters from the center of the star and is moving at a speed of 34.1 kilometers per second. Be careful, this is given in kilometers. At point Y, the comet passes its point of closest approach to the star. At this point, the comet is a distance of this from the center of the star. Okay. So apparently all the distances are given from the center of the star. And then the question says both the comet and the star can be considered as point masses at their centers. Okay. Calculate the magnitude of the change in the gravitational GPE of the comet as it moves from position X to position Y. This is an easy part. We just need to find the change, right? So the comet is this from the center of the star and is moving at this, and the closest approach, we have some distances given to us. So let me just identify all the parameters that are given that I'm going to extract from this question, and I'm going to mention it over here, and then we'll work this question out together. So there you have it. I've mentioned the distances from the centers of the star and the center of the comet. This is the distance initially, and this is the distance when we are at Y. So it's a matter of it's a simple matter of just finding the changes and the potentials, and then finally multiplying it by the mass of the comet, and that should give us the change in potential energy. So let's just do it. Let's just pull it off. And the thing is, I need to zoom it out a bit so that I can refer to the diagram as well as all the data and then work this out. I'm going to zoom in afterward. So let me just first copy the data that I already have. So first of all, we need to work this out. Calculate the magnitude and the change of the gravitational potential energy of the comet as it moves from this. So this is going to be change in GPE, gravitational potential energy, is going to be equal to, so that is going to be change in phi itself multiplied by the mass of the comet. Okay, so this is what we are going to be doing. So mass of the comet itself multiplied by the change in the phi values. So this is going to be minus, it is less negative as it is away, so minus gm. This is going to be the mass of the star itself. So mass of star divided by the distance, which is 8.44 into 10 raised to power 11. And I'm just going to then we have, since we are finding the change, that means we are going to have a minus sign over here. But then again, the other potential is also more negative. So that is why we are going to put a minus sign again over here. So this is going to be G, mass of the star, divided by the distance. The new distance is actually 6.38 into 10 raised to power 10. Okay. So finally, I'm just going to close this bracket. And I'm also going to put another bracket over here. This makes sense. In fact, I can take GM as common. It पूरा का पूरा GM ही बाहर निकाल दो तो हो जाएगा हमारे पास. So let's just work this part out. I'm going to be inputting the values over here, and I'm going to be doing this calculation in one go. So give me a minute. Let me just solve it. So there you have it. This is something that I have done. And yes, this is a very involved calculation, and I have done it directly using a calculator. You can clearly see that what I did was that I took GMS as common. मैंने directly इनको बाहर निकाल दिया, और इसके अंदर जो माइनस जो साइन थे मैंने वैसे इंटैक्ट रखे. So finally, it was just a matter of solving it, inputting the values into the calculator and doing it. Remember this thing, whenever you're using a calculator, at least do it twice so that you know if you have made any mistake or not. Just be very careful with the calculations. This was very lengthy calculation, by the way. So that does it. So this is the value that I'm getting. So I'm just going to write it down as 4.23 into 10 raised to power 23 joules. Okay. I don't need to mention the unit because it's already given. Okay. फिर मुझे कह रहा है state with the reason whether the change in gravitational potential energy is an increase or a decrease. This is definitely a decrease. State with the reason. We need to state the reason. So this is going to be a decrease. This is going to be a decrease. This is the first statement. Whether the change is an increase or a decrease, it is a decrease. Decreases. And we need to state why. So actually I'm just going to, the main idea is that the gravitational potential energy is itself is a change, but then again we are coming closer, so that means the GP is actually decreasing. So I'm just going to write it down. First of all, I'm just going to write it down. The force is attractive. Gravitational potential becomes more negative. Right? Becomes more negative. It's a common sense. Becomes more negative. Gravitational potential becomes more negative. So the gravitational potential energy, actually decreases. Right? Force is attracted. Gravitational potential becomes more negative near the star. Okay, so that is it. Okay, use your answer to determine the speed in kilometers per second of the comet at point Y. Okay, this is going to be a lengthy question once again. Use your answer in B1 to determine the speed in kilometers per second of the comet at Y. The thing is, it already had some speed and more speed is going to be added. That is going to happen. And we need to work this out. Let's just look at this question first. Let's see what data do we have. We initially had some kinetic energy because it was apparently moving at the beginning, which is 34.1 kilometers per second. Obviously it is moving again at Y, but there is a definite change in the gravitational potential energy. It is going to be much faster at this position. That's for sure. That's for sure. So what we need to do is that how do we come about this thing? So first of all, the change in GPE must have converted to kinetic energy. That is what I'm going to be doing, right? And we can work it out. Let's just pull this off. So let's begin. I'm just going to construct an equation and then I'm going to explain it how to do it. This is what I'm going to be using. You can clearly see that there is a definite change in potential energy, and also there's going to be a change in kinetic energy. So we are going to be pulling this off. So 4.23 into 10 raised to power 23, and this is going to be half m. And then first of all, we already had some speed initially, and that was 34.1 kilometers per second. So let's see. Let this be the initial speed. We need to find the final speed, right? So I'm just going to write down v whole square, and therefore minus 1 over 2 m. This is the mass of the comet itself. So multiplied by 34.1 into 10 raised to power 3. That should convert it into meter per second, and therefore square. This is what we are going to be doing, right? So this becomes 4.23 into 10 raised to power 23. I'm just going to input the values and solve it. 1.2 into the mass of the comet is actually 2.2 into 10 raised to power 14. Okay. So this is going to be 2.2 into 10 raised to power 14 multiplied by v square. This is the value that we require. And minus half times this is going to be again 2.2 into 10 raised to power 14. I could have taken this as common, but let's just make this becomes more clear this way. So 34.1 into 10 raised to power 3 raised to power square. Okay, so let me just solve it and let's find the answer. Okay, so this is the value that I'm getting. Initially, I got the answer as 70,800 meter per second, and I converted that into kilometers per second. So this is the answer that I'm getting. So this is going to be 70.8 kilometers per second. So we don't have to mention the unit over here, but it was important that we had to convert this into the correct unit. Okay, let's just move on to the last part. A second comet passes point X with the same speed as the comet and this, and traveling in the same direction. This comet is gradually losing mass. Okay, that is important. The mass of this comet when it passes point X is the same as the mass of the comet NB. Okay. Suggested with the reason how the path of the second comet compares with the path shown in figure 1.1. If we look at this equation, if we look at this initial equation, the entire equation that we used to calculate this thing, I need to construct this equation again. So we have change in GPE is equal to change in EK or KE for that matter. And we know that GPE is actually equal to phi m, change in phi m, which is equal to change in half m. This is going to be V final square minus V initial square. We can see that the mass actually cancels out. If the mass is getting cancelled out, that means the path would remain the same. Suggest with a reason how the path of the second comet compares with the path shown and it remains the same. Remains the same. Same as mass gets cancelled out. You can show this working in the examination, right? So that is it. The question that we are going to be solving, and we have already done this part, so I'm not going to waste my time with this. Let's just go to this question. An isolated solid sphere of radius r may be assumed to have its mass m concentrated at its center. Okay. The magnitude of the gravitational potential at the surface of the sphere is phi. Okay. On figure 1.1, show the variation of the gravitational potential with distance d from the center of the sphere for values of d from d is equal to r to d is equal to 4r. Well, you must understand that the gravitational potential follows the inverse law, not the inverse square law. Okay, so that is important. We already know that gravitational potential phi is actually equal to minus gm over r. Actually, I'm just going to write it down. Phi is actually, let's suppose, directly proportional to gm over r. Okay, so we have it. And the inverse square law states, sorry, inverse square, no, not in the inverse square law, inverse law with the distance states 1 over r. So there we have it. Now we need to plot this. An isolated solid sphere of radius r may be assumed to have its mass m concentrated at its center. The magnitude of the gravitational potential at the surface of the sphere is phi. Okay. On figure, show the variation of the gravitational potential with distance d from the center of the sphere for values of d, r to d is equal to 4r. So that is simple. We can do either way. We can. It's a 3-mark question. So let me just read it again. Since this is an attraction case, the potential actually becomes more negative at the bottom, or maybe at the I need to rephrase this word, rephrase this sentence. The idea is that the potential tends to increase as we move away from a certain planet. So near the surface, the potential is going to be more negative. I'm going to follow that the same rule over here. I'm just going to worry about this thing. So let's see. At r, the potential is actually minus phi. Then at 2r, this is going to be half of that value. So we can check this out. So this is actually gm over 2 times r, and therefore gm over r is actually 1 over 2. So that is going to be half of this value. And immediately at 3r, this is going to be 1 over 3. So 1 over 3 is actually 0.33. So this is going to be 0.33. So let me just look at this thing. 0.1, 0.2, 0.3. This is going to be 0.4. So 0.33 is somewhere over here. Anyways, I'm just going to mark this over here. And 1 over 4 is 0.25. 1 over 4 is actually 0.25. So this is going to be 0.25. So let's see. 1, 0.1, 0.2, 0.25. So this is it. This is 1 over here. So the potential curve is going to be like this. And one solid curve. I hope this is clear. This is done. This is a 3-mark question and this is done. Anyways, we have to start from R so we don't go back. The potential is actually we don't care about that, what happens inside. So let's just move on to the next part. The sphere in this the sphere in B is a planet with a radius r of 6.4 into 10 raised to power 6, and the mass m is actually given to us. The planet has no atmosphere. Okay. So a rock of mass moves directly towards the planet. It is moving towards the planet, that therefore the value of the potential is going to become more negative. Its distance from the center of the planet changes from 4r to 3r. Calculate the change in the gravitational potential energy of the rock. This is a rather simple question. We just have to do that. So change in phi m is equal to the change in GPE, gravitational potential energy. So we need to find this. So therefore change in potential energy is actually equal to change in phi. So the mass, the sphere in B is a planet with a radius this and a mass of this. The rock of mass, so this is going to be this is given to us 3.4. This is the m. So this is going to be 3.4 into 10 raised to power 3 multiplied by, we have to find this. So this is going to be, this is moving from 4r to 3r, so it is becoming more negative. So we are going to find this change. So we need to find this change, calculate the change in this energy of the rock. So the value is going to become more negative. And I'm just going to go with less negative first. So this is going to be, the answer is going to be automatically negative. So 1 over, I just took this mass as common. I should also do this gm over r, which is actually 4r initially. And then minus minus plus gm over 3r. So there you have it. I'm just going to take gm as common. So this is going to become 3.4 into 10 raised to power 3 multiplied by 6.67 into 10 raised to power 11 multiplied by the mass m, which is given to us as 6.0 into 10 raised to power 24, which is actually the Earth. 6.0 into 10 raised to power 24. And this is going to be 1 over 3r minus 1 over 4r. So there you have it. And we need to solve this. So r is given to us. We just need to input the values and let's get an answer. The r value is actually this. So we need to input these values over here and over here. So there you have it. Let me just solve this. I'm going to pause this video so that I can peacefully do the calculation and pull this off. Actually, I just made a mistake over here. This is multiplied over here. This is a multiplication sign. Okay. So there you have it. I'm going to pause this for a minute. So finally, I'm getting a value of 1.8 into 10 raised to power 10 joules. Okay. So there you have it. 1.8 into 10 raised to power 10 joules. Explain whether the rock speed increases, decreases, or stays the same. Okay. First of all, we need to realize that there is a definite loss in potential energy because it has become more negative. So actually I'm just going to write it down. The potential energy decreases, so Ke must have increased, so speed increases. I guess that's it for today. These are some of the questions that we did today. We did some of the most difficult questions over here, and I think that was fun. We are going to be doing another chapter next time. Anyways, guys, take care. अपना बहुत बहुत ख्याल रखो. Allah Hafiz and take care, guys. Take care, all of you guys.